All right, so hello everyone. I'm Norman Wahlberger, and today we're going to start on a few lectures on the contributions of Gauss to differential geometry. So Carl Friedrich Gauss was one of the giants of modern mathematics, and his dates are 1777 to 1855. And he was a German mathematician who had very wide interests, who did very important work in number theory. He was interested in physics. He was interested in astronomy and became a sort of a royal astronomer. And he eventually became involved in geodesic or geodetic surveying. So he got a job sort of as the royal surveyor of his province of Hanover. How do you spell it? And maybe there's only one N. And this involved going out in the summers with on horseback and going all around and sort of triangulating the countryside and figuring out where exactly everything was. And perhaps as a result of his work in surveying, and maybe also as with the influence of his work in astronomy, and in particular sort of the idea of the celestial sphere. In any case, he put together a very important foundational work in differential geometry, which he wrote in 1827. So already he was no longer a young man at that time. And it's called Disquisitiones Generales circa superficies curvas. Okay, as you can probably guess, this is not German. He wrote in Latin still at this time. And this is a foundational paper in which he really gave new directions for the subject. And we're going to talk about some of his contributions in the next few lectures. So let's start with just a picture. So here's some kind of surface. We'll make it a closed surface. And we'll call the surface S. And here's the point P on that surface. And we've seen many times that it's important to look at the tangent space to the surface at P. So here's this tangent space. To the surface S at the point P. And might give this a more familiar name or notation. So this is sometimes called T sub P of S. All right, this is of course a plane in the three-dimensional space that we're in, but more than that, it's naturally a vector space. So this is naturally a vector space, only two-dimensional. In other words, it's natural to consider vectors that are emanating from the point P lying in this direction, because those are the tangents to curves that are on the surface through P. If we take some curve that lies on the surface, say alpha t, then its derivative at P will be one of these tangent vectors. So alpha prime at, whatever point corresponds to P for that curve. Okay, but in general, there are no really natural coordinates on this plane. It's not as if this plane comes with x and y coordinates. It's really just a plane, and we can impose coordinates on it, and but there's not really a natural or obvious way of doing that. So there are no natural coordinates on this tangent space. But there is a natural inner product. But there is a natural or canonical inner product. Namely, we just take the ambient inner product in our three-dimensional space. So here's our three-dimensional axes. This is all happening in three-dimensional space. So if we have some vector v in the tangent space, then we can define the quadrants of v just to be v dot v, where the dot means the dot product in the big space. So in other words, we can restrict the dot product from the three-dimensional space, the Euclidean dot product, to our tangent plane. And this is sometimes called the first fundamental form. First fundamental form. And when we say form, we mean quadratic form, i.e. quadratic form on this two-dimensional space. And it's independent of parametrization. Well, one of Gauss's very big ideas is that we should introduce a surface, or think of the surface parametrically. So Gauss introduced the idea of describing a surface like S parametrically. And that means that we have some other plane, usually, say, the UV plane, and perhaps we have some rectangle in that plane. And we think about our surface here in three-dimensional XYZ space as being the result of a map, like a chart, from this UV plane into the surface. So there is a map, that's denoted by R, or just R. So there's a map denoted by R, which takes this rectangle with its natural grid of lines parallel to U and V to a part of the surface. It doesn't have to be the whole surface, of course, but to some part of the surface. And naturally, these lines are going to get mapped to some more general curved lines over here in the surface S. All right, so this allows us to think about the surface in terms of coordinates. Here then are the coordinates, and then we can transfer various things from the surface to this rather rigid, quite controlled area. Now, in particular, we can take two directions. Let's say we're interested in a particular point over here. Say that happens to be the point P that we're interested in. And maybe it comes from a point Q over here. Or maybe R over here. And then we can take the two natural tangent vectors over here, namely the vectors in the U and the V directions. And we can see what their image over here is going to be. Well, they're going to be little vectors that are tangent to the surface at P along the curves, which are the images of these U and V lines. So once we have such a parametrization, so given such a parametrization, then we do have canonical vectors in this tangent plane at P. which we might denote in red. So there's be the tangent plane at P. And now these two vectors are sort of canonical vectors in there that are coming from the particular chart given by this function u. So this was actually not entirely original. I mean, actually Euler was the first person to have introduced the idea of describing a surface parametrically, but Euler didn't do that much with it. But it was really Gauss who took this idea and used it as the foundation for his treatment of surface theory. Okay, so for example, this inner product that we have over there, if we call these vectors, let's say R1, which is dr by du, or maybe I'll write r sub u. So r sub u is the derivative of this vector valued function in the u direction. That'll be one tangent vector. And another tangent vector would be r sub v. That denotes the partial of r with respect to v. Okay. So r sub u and r sub v are natural basis vectors of the tangent space of P at S, given the parametrization R. And so then it becomes, if you have a general vector, then a general vector in the tangent plane, say V, can they be written as a linear combination of those guys? Let's say x times r sub u plus y times r sub v. Okay, so these are the coordinates of a general vector, say V, with respect to the basis r sub u and r sub v in the tangent plane there. So then in terms of these vectors, if we take the dot product, so then the first fundamental form, v dot v, is going to look like, well, if we just expand this out, x times r sub u plus y times r sub v dot x times r sub u plus y times r sub v. Now this is just the dot product in the ambient big three-dimensional space that we're in. Then we'll see, just using the bilinearity, that this can be written as, well, I might write it like this, as e times x squared plus 2f times xy plus g times y squared, where e is, by definition, r sub u dot r sub u. F, capital F, is going to be r sub u dot r sub v, which of course is the same as r sub v dot r sub u, because it's symmetric. And g is equal to r sub v dot r sub v. And we can think about these three as numbers. These are numbers associated to the point P. Or we can also think of them as numbers associated to the point R. Okay? So these numbers E, F, and G depend on the point P in S that we're starting with, or the point R in the UV plane, where R of capital R is equal to P. So in particular, we can think of them, if we like, as functions over here in the UV plane. So they can be viewed as functions on the UV plane. Yeah?
That condition on F, where r sub u dot r sub v equals r sub v dot r sub u, does that mean that we're assuming the surface is smooth?
No. So this dot product here is just the ambient dot product in three-dimensional space. So that I shall say. So what we're talking about here is just the dot product that looks like this, that x1, y1, z1, dot x2, y2, z2 is x1, x2 plus y1, y2 plus z1, z2. In other words, the familiar dot product in three-dimensional space. That's the where we're getting our distance or quadrants notions from. And we're just restricting that dot product to the tangent plane and then expressing it in terms of the coordinates that are obtained from this particular parametrization. So these three functions, e, f, and g, we can think of them as functions on our parameter space. They become important functions for Gauss. There are the functions that basically determine the first fundamental form. Knowing e, f, and g is really the same as knowing the first fundamental form. Okay, so that's good. That's the kind of approach that Gauss took. And so the tangent plane is of obvious interest. And there's something else that's canonical associated with this point P, and that's the normal to the tangent plane. Okay? That's sort of another obvious thing that's around the normal vector. Normal, say n, to the tangent plane. So, right over here. So, another important canonical object at P is the normal vector to the tangent plane. And if we agree to normalize so that normal is of unit length, then it's almost completely canonical. So we'll define n of P to be the unit normal at P pointing in the outside direction. Okay. Pointing outside, pointing outwards. So that assumes that we have a surface actually which is the kinds of surface that we're interested in, where we have an orientation, so there's a well-defined notion of outside of the surface, and so we're always going to take our unit normals to be in that outer direction. And then there's only one such normal which is exactly of unit length, and we're going to call that n of P. So given a point P, n of P, there it is right there, is going to be the unit normal pointing outwards. And of course that doesn't depend at all on a parametrization. But we can describe it in terms of a parametrization. Okay? We can describe it in terms of a parametrization because to get a vector which is perpendicular to the tangent plane, we can take the cross product of the two vectors in the tangent plane. And we have the two vectors, here they are right here, so r sub u and r sub v are the two vectors coming from the parametrization. They may not be perpendicular, they may not be the same length, it doesn't matter. There's still two vectors in the tangent plane, so we can write n of P as r sub u cross r sub v, suitably normalized. Of course, we have to divide by the length of r sub u cross r sub v. It's a bit painful because there is a square root involved in that length. For sure. Okay. So there's some irrationalities that we really can't avoid with talking about this unit normal. That's the same kind of story that we saw with the Frenet frame when we were talking about the curves and the Frenet formulas. Sometimes it's a little bit hard to actually get nice explicit forms, but nevertheless that's a good formula. So n of P is the unit normal. And then Gauss had a very simple idea. He said, okay, well what we really have here is a situation where for every point there's a unit normal. Every point on the surface has a unit normal. So why don't we put all that information together? There's really another map floating around here. Okay. And maybe I will draw it here. So this is the Gauss map. It probably should be called, there was another mathematician, Rodriguez. So let's call it the Gauss-Rodriguez map, okay, which is a map, and we'll just denote it by n, which is a map from the surface, S, that we're starting with, to the unit sphere. So S2 will be the unit sphere in three-dimensional space. And the map is just the map that takes n, or n sends a point P to this unit normal that we're calling n of P. So over here perhaps is the 2-sphere. And we can think of it in the same space or not, doesn't really matter. So there's a point P. The unit normal, say, in this direction is down here. So if we translate that normal, so it's centered there, then we're going to get a point on the unit sphere. And that point is n of P. So we can think about mapping this point P to the point n of P on the unit sphere, which is just the point that tells you what direction you have to go in for the normal. So here's where Gauss may have been motivated a little bit by his astronomical expertise, because in astronomy we're basically on planet Earth, everything is a direction. So everything, the crucial thing is all just directions from Earth. And that's sort of what's happening here. So given P, what's the direction of the normal? Then you think of just translating that direction so that it's from a fixed point. So we can compare all the different directions. Okay, so this fellow Rodriguez actually introduced this, defined this in 1815. It's just the map that sends P to the unit outer normal. Oh, this is kind of an interesting map. And one sort of natural thing to ask when you have a map like this is, what does its derivative look like? What does its derivative look like? So the derivative is a linear approximation to the map. So let's say we're just near P. We're just concerned with neighboring points. Well, clearly, if we're near P, the normal is going to be near n of P. But the tangent plane here, the tangent plane to P, is of course by definition perpendicular to the normal itself. And the tangent plane to n of P is the tangent plane to the sphere at that point. That's also perpendicular to that vector, because any point on the sphere is always perpendicular to a radius. So the tangent plane to the surface at P and the tangent plane to the sphere at n of P are essentially the same plane. They're in the same direction. All right, so here's the tangent plane to n of P of the 2-sphere. And these two planes are parallel. So note that the tangent plane at P of S is more or less really equal to the tangent plane of the sphere at n of P. These two planes are parallel. So as vector spaces, they're really the same. And that means that we can think, if we like, of the derivative of the the normal map, will send this tangent plane to this tangent plane. Okay. So whenever you have a mapping from one surface to another, the derivative is the linear approximation to it. So here we have some surface, say S, and here we have some other surface, M. It's a completely general story. And we have some point P here, and we have some function, maybe F. Okay, so suppose that F sends point P to, say, Q. So there's F of P. Okay. So at P, there's a tangent plane. At Q over here, there's a tangent plane. Now, if you go in some direction from P along some tangent vector, if you choose some tangent vector at P, say that direction there, and you proceed to go in that direction, you're going to get a little curve. And then if you ask yourself, well, what's the image of that curve? Under the map F, you're going to get a corresponding curve over here, and it might, of course, be in quite a different direction. But it will have a certain direction at Q. So there will be a certain direction that's determined. And then the derivative, so if F is a map from S to M, and F of P happens to be Q, then the derivative is often denoted dF. Okay, so dF is then going to be a map from the tangent plane of S at P to the tangent plane of M at Q. And the point is that that's a linear map. We throw away all higher powers. We're just interested in the linear terms. This is a linear map. So that's a very general situation that, really you study in calculus of several variables. So going back to here, to this particular situation, we have the normal map from the surface S to the sphere S2. The derivative then, so dN, well, at the point P, is going to be a map from the tangent space to S at P to the tangent space of N of P at S2, which is really the same as the tangent space of S at P. So the derivative can really be thought of as a linear function or linear map from the tangent space to itself. You don't have to think about this, but you can. Okay? So this can be viewed as a linear map on the tangent space at S. And in terms of this, Gauss realized that the curvature had a very simple geometrical explanation, which on the surface is quite different from Euler's sectional curvature kind of approach. So Gauss realized that the Gaussian curvature, well, he wouldn't have said that maybe in that way. The Gaussian curvature, what we're calling K2, or what's often just called K, which in Euler's language is the product of the principal curvatures, can be interpreted or can be obtained by the formula that K equals the determinant of this map dn at P. So the curvature at the point P, maybe I'll say, the curvature at the point P equals the determinant of this linear transformation. So it's a Jacobian. It's a Jacobian. So we're having a transformation from one two-dimensional space to essentially the same two-dimensional space. And that linear transformation distorts areas generally. The amount that it distorts areas is measured by the Jacobian. That Jacobian is a determinant. It's really the determinant of the matrix that represents that linear transformation. And the determinant of that is another way of thinking about what the curvature is. Okay, so before we compute this, let's have a look at some examples of this Gauss map to get a bit more intuition about what it's like. This Gauss-Rodriguez map. So the first example is a very simple one. Let's say that our surface to begin with is a sphere of radius r. So S is a sphere of radius r, not necessarily a unit sphere. So here we have a sphere of radius r, and over here we'll draw the unit sphere that we're mapping to. So there's 1. So here's our S2. Okay, we'll choose a point P up here. It's pretty obvious what the Gauss-Rodriguez map does here. If we look at this vector joining the center of the sphere to the point P, then the normal's in the same direction. Okay, so the normals is in the same direction, n. And so when we map P to the normal, we'll just be going in the same direction, but a little bit further or less because it's got to be a unit. So n of P, in this case, n is just scaling. So if we have some little, say, circle around P, and we're interested in, what's the Jacobian of this transformation? So a little circle around P will be sent to another circle around n of P. Okay, and as we go around this circle in the, say, positive direction, well, the image is going to go around this circle also in the positive direction. And if I denote the area of this circle, say by dA, maybe dA sub s because it's on the surface S, and over here I'll denote this little area by dA of S2, so the corresponding part of the surface there. And here is our Gauss-Rodriguez map, N. Well, then, so N is just scaling by how much? By, well, it's going from a sphere of radius r to a sphere of radius 1, so scaling by 1 over r, which is also, okay, 1 over r, which is the sectional curvature there. Scaling by 1 over r. So the ratio of areas, dA of S2 over dA of S, will be 1 over r squared, which is the curvature of the Gauss curvature of this sphere. K equals K2 of S. Here's another example, a little bit more complicated, where we look at a surface which is like one of our negatively curved, like hyperboloids. Okay, so maybe we choose a point P over here, and it might have one principal curvature like this, another principal curvature, line of curvature like this. Okay, so here's our surface S over here, and again, here's our two-sphere, the unit two-sphere over here. All right, so let's try to see if we can visualize what happens to this normal as we move around P. That's what we're trying to study. How does the normal depend if we move around the surface S a little bit? So at P, we have a normal direction. Maybe I'll try to denote that there. So there's the normal at P. Okay, so the normal map just takes P then to this corresponding point here, so that vector and that vector are exactly parallel. And now let's have a look at a small circle or a little loop around P. So we'll draw a little loop on the surface. And I remind you, P is just at this sort of saddle point. So in one direction, P is at the bottom of a valley, but in the other direction, P is sort of on top of a pass. Okay. So this circle goes sort of up and down. Okay, so let's try to draw some normals at various points. To make that a little bit simpler, let's label some of the points. Let me label this one, say, A, and this one B, and this one C, and this one D. Okay, what are the normals going to look like? The normal at A is going to be sort of in this direction. The normal at B is going to be sort of more in this direction. At C, it's going to be like in this direction. And at D over here, sort of more in this direction. So as we go around here, what happens to the normals? The normals are going to be moving around N of P, making some circuit around there. And at A, the normal's sort of tilted this way. So maybe I'll write it, this might be normal of A. And then at B, the normal's in this direction. So that's sort of like that point there. And then at C, the normal's in this direction. So that's sort of over on this side here. And at D, it's pointing in that direction. Okay. So over here. So the point is that as we go around this little neighboring circle of P in the positive direction, the normals are actually going around N of P in the opposite direction. You can convince yourself that by taking your hand, the crook there of your hand is a good place that's a saddle point. If you just think of the normal directions, here's normal. Just sort of think about what happens to the normals if you just sort of sit there quietly with a pen or something like this and sort of imagine what happens as you go around in that direction, what happens to the normals. So you'll kind of see, well, maybe I can kind of do it. So as I go around in this direction of the point, the normal is going like this. Maybe you can see that that's sort of going in the opposite. If you just look at the direction of the normal, it's going in the opposite direction as the loop is. So a small circle has its orientation reversed by our Gauss-Rodriguez map. Okay, there's a third example which is sort of in between these two, where our surface is parabolic, like this. It's like a sheet of paper that's bent like this. And at some point, say P on that side, well, there's one line of curvature that goes like this, but the other line of curvature is straight. So one of the principal curvatures here is 0. So it's a place where the curvature is actually 0. And if we look at the image of the Gauss map in a little neighborhood of P, what are we going to find? Well, first of all, where is n of P itself? So here's P, and so maybe the normal is in this direction, so perhaps n of P is right here on the surface. And if we move along this portion, or along the actual curved part, the normals will certainly change. So here they'll be there, and here they'll be there. So as we move along this portion here, the normals will move along some arc. Say from A to B, here's n of A and n of B. But then if we look at what happens at points where we move in the 0 curvature direction, the normals are all the same. So if we move along this direction here, the normals are all parallel to what they were at P. So this entire strip, that straight line, all the normals there get mapped to the same point. There's a collapsing going on. Everything here just gets mapped to n of P. And similarly, sort of on some other parallel line, all those points get mapped to some point there. So the net effect is that entire little circle gets mapped by the Gauss map just to this little curve on the sphere. So the Gauss map actually collapses things. So n collapses S onto a curve in S2. And so certainly the ratio of areas is going to be 0. Right? If we're interested in the ratio of this area, dA of S, and the ratio here, dA on S2, well, this ratio is going to be certainly 0 because the numerator is 0. And that is, in fact, the curvature at the Gaussian curvature at P. So we have these 3 different kinds of behavior of the Gauss map, the Gauss-Rodriguez map, the map that takes a point on the surface and associates to it the normal direction on the unit sphere. And I guess the negatively curved region here is characterized by the areas changing orientation, while at some elliptic point here, the orientation is positive. And the parabolic points are sort of in between the elliptic and the hyperbolic points. There the curvature is 0, and the derivative of the Gauss map collapses. It's no longer invertible. So this already raises a few interesting questions. So an obvious, interesting question here is we can separate points on a surface into those where the determinant is positive, the determinant of the Gauss map is positive, and those where the determinant is negative. Into elliptic points. So here, that's where the determinant of n of p is positive, and hyperbolic. Points, that's where the determinant of n of p is negative, or the Gaussian curvature is negative. And in between, we can expect curves of parabolic points. Parabolic points are where the determinant of n of p is 0. And so natural question is, what do these parabolic lines look like? What do the parabolic lines, say, on your hand look like? Okay, so if you take your hand, there's obvious places where the curvature is positive. For example, at the end of a finger. In that case, the sectional curvatures are both in the same direction. The surface is on one side of the tangent plane. The Gauss map has positive determinant. On the other hand, if you choose some point like here, what we were mentioning, this is going to be negatively curved. So there's going to be you can see obvious places where there's negative curvature. There's obvious places where there's positive curvature. In between them, if we drew a map, there would be these curves of 0 curvature. And they would somehow crisscross your hand in some way that I couldn't say unless I thought about it more carefully. All right? It's sort of interesting that there are these things there. Okay, so Gauss appreciated that this particular combination of principal curvatures, K equals K1, K2, we're also calling that the second curvature in our little setup. This now also has the new interpretation of being the determinant of n of p. And this map, this n of p, you can think of that as being a map from the tangent plane to the tangent plane. This is sometimes called the shape operator. The shape operator at P. Okay, it has other names too, but I should say dnp, the derivative. The derivative is between the tangent planes, and that's the derivative we should put there. Determinant of the derivative of n of p. That's the Gauss's interpretation of the curvature, the Gaussian curvature. And then we have to mention this most important theorem in the subject, Theorema egregium, which Gauss discovered, well, probably at the time of his paper, around 1825 or something. But in this paper, is that this Gaussian curvature is an intrinsic. K equals K2 is an intrinsic quantity. What that means is that you can determine it purely by calculations on the surface. So these various considerations up till now, including these ones here, actually involve you going outside the surface, talking about normals in the three-dimensional space. Gauss realized that that the curvature actually was something that a bug that was just on your hand, making measurements on your hand, and could never leave the surface of your hand, could determine. Right? This is in dramatic contrast to that of a one-dimensional bug on a piece of string. A one-dimensional bug on a piece of string can never determine, just by local considerations, how curved the surface appears to us. But a two-dimensional bug on a surface can tell. It can't tell the mean curvature, or the first curvature, but the second curvature it can. And this is, for sure, the most important theorem in differential geometry. Okay. So we'll talk a little bit more about this and other aspects of this very interesting story next time.